All right, so welcome everybody to STA 101. That's Simultaneous Thermal Analysis 101. Today's session is meant to be quite broad in content, something from introductory theory to applications and best practices when you use the instrument. Just to introduce myself, my name is Hitoshi Taniguchi. I'm the subject matter expert in thermal analysis at C-Therm Technologies. And I'd like to begin with a quick introduction to our company first. So we are the world leader in thermal conductivity instrumentation, and we specialize in non-destructive thermal analysis solutions, particularly in the space of transient state thermal conductivity instrumentations. And our flagship instrument is this Trident thermal conductivity instrument. The design philosophy behind this instrument really is that it's just better options when it comes to thermal conductivity measurements. So we have 4 different methodologies, each specializing in different applications and use cases. But if you would like to inquire us more on that, you can always reach out to us directly. But for today's discussion, will be more geared towards STA, the thermal analysis side of things. So I'd like to jump straight into it. So I'll discuss quickly what we have in stock in terms of contents here. So I'd like to begin with some introductory content on STA in general. And then we'll go over some nice applications you can perform using STAs and a couple of measurement guidelines when you actually use the STA. So how to sample your materials properly, how to set the temperature profiles and such. A bit more practical guidelines would be discussed here. And lastly, we'll go into a bit more advanced STA applications. So one of the key things about STA is that you can modify and add more things into STA to make them more flexible to different applications. So we'll look into that as well. And we'll wrap it up with some Q&A session to answer some of your questions at the end. All right, so let's begin. Firstly, I'd like to go through some introductory theory on what is STA. So to start on this discussion, I think it's worthwhile to talk about thermal analysis in general first. So a huge sector of material science is dedicated to a simple question, and that is that what would happen to my sample at different temperatures? So that's thermal analysis in a nutshell, really. And for example, here, I'd like to take this example of wood. This is a picture I took myself, actually, at one of my outings with my friends. But just from this, very simple example of, everyday household items, it can ask so many questions as to, related to thermal analysis, like what temperature does the wood start to burn? How much heat is released, heat capacity of the wood, expansion and contraction during heating, mass loss during the combustion, and what kind of gas gets released during the combustion. So in order to perform thermal analysis, we have the big 3, or the 3 main representative methods when it comes to thermal analysis. So today's discussion will be on STA, so that's the first column here. You can see that the instrument covers quite a broad range of thermochemical reactions, from melting all the way to oxidation. DSC, on the other hand, has some limitations on things that involve decomposition or combustion due to the nature of the sensor, but it is more fine-tuned towards very subtle reactions like Curie point transitions or glass transitions, these kind of secondary phase transitions. And TMA is more or less dedicated to thermomechanical analysis, so something like glass transition, of course, but really its main forte is the centering, softening, or expansion, contraction study of the sample as you change its temperature. So coming back to the previous example, let's look at how many questions STA can answer out of this list, and the answer would be almost all of them. The green check marks represent the questions that STA can almost answer entirely, and the yellow check marks mark the ones that STA can either answer partially or with additional configuration. expansion and contraction is a little bit of a tricky one with STA, but you can sort of discern the thermomechanical change using sample observation, which we'll talk about today. And lastly, this question, the gas that gets released, can be analyzed using the method called evolved gas analysis, which we'll touch on briefly as well. So now that we've talked about what STA can do, I would like to discuss a bit more on what STA actually is. And STA stands for Simultaneous Thermal Analysis. And it's simultaneous in the sense that it performs two measurement modes simultaneously, and that is TG and DSC. TG tracks the mass change of a sample as a function of temperature. DSC tracks the difference in heat flow between a sample and a reference. So we'll give an information about the energetics of the reaction. So how much energy is released or absorbed, or what is the heat capacity involved in that temperature amps. A bit more into each component. So TG stands for thermogravimetry. Again, it's a technique where it tracks the sample's mass change as a function of temperature. As you know, when most chemical reactions involve mass change in some way, shape, or form. So, for example, this oxidation of iron corresponds to mass increase because oxygen binds into iron to form more heavier compound, iron oxide in this case. So the idea with TG is that by plotting the mass change as a function of temperature like this, if you see a dip in this curve, it means that the temperature mass is being lost in that temperature, and vice versa. If you see an increase in the TG curve, you see a mass increase. Another component of the STA is the DSC, which is differential scanning calorimetry. This is very common thermal analysis approach, and it measures the thermal events by monitoring the heat flow in and out of the sample. So the typical output from a DSC signal looks like this. If you have a flat DSC curve, it means that your sample is not doing anything. But if there's a baseline shift like this, or peaks or valleys as they call them, then you would know whether your reaction is endothermic or exothermic, and you can quantify how much energy is being released on each reaction. So, for example, on these dips here, they correspond to endothermic peaks, and those are corresponding to melting, evaporation, dehydrations, and such, and vice versa. If you see a peak, that's associated with crystallization, combustion, and oxidation, usually. So although we are, thermal conductivity company, essentially, we also supply thermal analysis equipment from Rigaku in North America. And most of our discussion will be demonstrated through their STA, which is STA Vesta. But you can kind of take this video as kind of like a demo for most of the STA systems available on the market. So most STA systems are comprised of this furnace, which is opening up here. For Rigakus, you can just press them once and it will just open up all the way. And these are sample holders. I'd like to pause the video very, very quickly. So these are sample holders that holds the sample, and this will double as the scale for the TGA, since TGA is a mass-related methodology, and it also doubles as the thermocouple. So that would give you information about DSC data that we talked about earlier. This right here is a sample pan. So this is where you would put in the sample. You would not put the sample directly onto the sample holder, and you would rest them onto the sample pan, sample holder like this. So the reason why there are two sample holders here is because Rigaku's STA uses a configuration called horizontal differential STA. So horizontal in the sense that the beam extends horizontally. So the furnace will come from the side and not directly from above. And it's differential in the sense that each of the sample holders stands for sample and reference side. The advantage of this is that any non-idealities present in the system already will be canceled out by having this reference side on being measured simultaneously. So it really helps with the resolution of the data and the stability of the baselines, as well as some practical advantages like if you have a horizontal STA, even if you drop your sample outside of the sample holder, there will not be any electronics staying directly underneath here, so you just have to recover it just by picking it up. So before we begin the measurement, you would close the furnace, as you can see here. And once it is fully closed, you can move on to the software, configure your measurement profiles, and begin your measurement. All right. So you might be wondering why there would be a need to combine those two methods simultaneously, why you wouldn't buy them separately, I suppose. And that is because you get a bigger picture of what's actually happening to a sample if you combine them both. So for instance, for this example, if you only had a TG, if you had an instrument called TGA, which only has a TG component, you would not see this endothermic dip that is showing up in the DSC. And if you only had the DSC, you wouldn't know that there's no mass loss actually happening to a sample. So by combining these two informations, we can draw the conclusion that there's no mass change and there's endothermic reaction. So there must be some kind of melting or other endothermic phase transitions happening at this temperature. So you don't have to confuse them for something like oxidation, or reduction that might incur mass change, which in this case is not. On the flip side, you might have an example where there is a mass loss and there's some exotherm happening, as you can see here. And by combining these two informations, you can deduce that the sample is going through some kind of combustion or decompositions at this temperature. So you won't have any confusions as to crystalline formation that is also exothermic or other exothermic reactions, because you know for sure that there is mass loss happening. This is sort of like a cheat sheet, if you will, of all the STA combinations. So by looking at this combinations, you can quickly discern what kind of sample reaction your sample is undergoing at that temperature. So now that we've looked at the theoretical side of things, I'd like to show you a couple of quite a nice applications you can do using STAs. This is really a classic example, using an STA as both a TG and DSC instrument at the same time, which it's really meant for. So in this case, we're measuring cement from room temperature to 800 degrees C. We have some measurement conditions here. We would touch a bit more on this and why this is very relevant, but for now, let's just look at the TG and DTA plot here. So on the green plot here, which is the TG, you can see multiple mass loss happening at different points, but the major ones can be discerned from by looking at the DTG curve, which is derivative of the TG as a function of temperature. So when there's a big change in the DTG curve, that's when you kind of understand that there is a major transitions happening. And this is also confirmed in the DTA curve here. DTA is simply pre-calibrated version of DSC. I'll talk about a bit more in detail later on too, but you can kind of treat it the same as DSC for now. And by taking these mass loss percentages and doing some high school style calorimetry, you can discern that there are this much calcium hydroxide present in the cement, and therefore this much calcium carbonate present in that cement sample. So you can perform these kind of quantitative analysis on the mass loss of the sample using STA. Another benefit of having an STA is that it's quite robust in terms of instrumentation. So you can do quite a lot of creative things with your sample. One of the examples is that you can put on a humidity generator with your STA, so you can study your sample's behavior as a function of humidity, for example. So in this case, we observed wooden chopsticks combusting at different temperatures depending on atmosphere, which is to be expected, right? If you have a sample that is more moist, or in our day-to-day experience, if you have a wood that is more damp, it takes longer for it to burn because of the excessive moisture that it's containing. So this is directly reflected in the observed STA curves here. The TG curves, which is the mass loss percentages, ultimately reaches the same amount for both dry and 90% relative humidity atmosphere, but the actual combustion point is shifting a bit later for samples with higher humidity. And lastly, this is something quite new that Roku has enabled through the development of STA Vesta, but you can attach the refrigerated cooling unit with the STA to perform this kind of cool heat kind of measurement, especially for samples that react at really low temperatures. In this case, we are looking at MOF sample, that is HKU-ST-1. I believe that's a copper-based MOF. And as you can see, depending on where you hold the sample at, in terms of the lower end of the temperature, the amount of carbon dioxide that it absorbs vary almost linearly. So to kind of go through this data a bit more here, what they did was they first set up the measurement under helium atmosphere, and they chilled it down to whichever temperature that's shown here. So for example, in this ramp, we set it down to negative 29 degrees Celsius roughly. And once we reach that temperature, we switch the atmosphere to carbon dioxide so the MOF can absorb the carbon dioxide at that temperature. And once absorption is done, they switch it back to helium again, and they did the heating cooling cycle once again to for MOF to release all that carbon dioxide that it absorbed. And through this study, they were able to plot this fairly nice linear plot of absorption percent versus the operating temperature of the MOFs. So this is one of the neat ways that you can use your STAs with. All right, now that we looked at how STA works and how it can be used, let's talk about practical things now. And I'll try to give you as much guidelines and tips and tricks to performing successful measurements using STAs. And it really all boils down to these 5 main points. So before you start your measurements, you need to figure out these 5 major points, which are the sample pan type that you're using, how you're going to prepare your sample, the heating rate that you're going to use for the measurement, any calibration requirements that you might need to fulfill before you run them, and lastly, the measurement atmosphere, depending on type of reactions you want to see with your measurement. So in terms of sample pan types, it really depends on the manufactured specs, but for most STAs, we see these 5 types of pan being used across all manufacturers. So something worth noting is that with each pan variants, you might have CU variants or crimp variants. For aluminum, they're very flexible in terms of the configuration, but when you come down to aluminum or platinum, you might only have open only, meaning that you can just put the lid on top of the pan, but you cannot crimp them because of its limitations. Another thing worth noting is the operating range of each pan. So aluminum can only go up to 500 degrees C, but alumina and platinum can go up to 1500, and silicon dioxide, that's quartz. Quartz can go up to 1000 degrees C. And for very high pressure applications, stainless steel pans are usually used. And the main 3 things to consider are the operating temperature, as I mentioned earlier. And this is perhaps the most important part, which is the sample reactivity with the sample pan. So this is typically not a concern if you're working with organics, but if you have metallic binders or you're working with some kind of inorganic salts, you might want to consider looking at using alumina instead of platinum, for example, because platinum can react with those components at very high temperatures and form different alloys, which will then contaminate your measured data. So this is something you have to consider quite carefully. And lastly, funnily enough, thermal conductivity of the material for each pan really comes into play when it comes to STA, because the quality of the data that you collect really depends on how fast or how well the heat response from the sample can travel down into the thermocouple, or a sample holder in this case. So if you have something like alumina or quartz that has poorer thermal conductivity than the metal pans, you might get less resolution when it comes to the DTA or DSC signals that you might be getting. So whenever possible, I would suggest using platinum pans. But if you must, if your sample is known to react with platinums at higher temperatures, alumina can be used. But otherwise, if you're going below 500 degrees C, aluminum is almost the go-to option. There are very rare occasions that you won't be using aluminum in such cases. All right, second point to consider is the sample preparations. So like I mentioned, the sample should go into the sample pans first in order to perform STA measurements. So if you have a sample that's a little bit bulky, like the styrofoam insulation here, you must prepare them in a way that the sample can fit inside the sample pan. You can do this in many different ways. If your sample is cooperative, let's say, like styrofoam, you can simply tear them apart and put them in the pan. But if your sample is something like a rigid polymer, like PET, for example, you can cut them using box cutter or lab knife and such, but please ensure that the heat from the machining process or cutting process does not alter the sample properties, since that's what we are trying to measure in STA primarily. The second point to consider is that the sample should make a flat contact with the bottom of the pan whenever possible. So if you have something like powders, it's generally a great idea to pack them, since the quality of the contact between the pan and the sample will dictate how well your DSC signals are going to turn out. If you have blocks or pellet samples, if it's possible, you should cut them in half like such so that you have a flat contact surface. If not, you should try your best to sand them off or cut them in a way that there's a flat contact surface. Otherwise, it might affect your measurement results negatively. And lastly, as for liquids, you should try to make it centered in the middle of the pan and not make it skewed towards either side of the pan. This is so that you get the best resolution in terms of data. And if you have a very viscous sample like honey, for example, try to dispense it at the center of the pan so that they spread evenly throughout the pan. And lastly, you should also consider the amount of samples you're going to use for STA measurements. So the general guideline is that you should make your sample fit within few milligrams range to tens of milligrams range. If you get below 1 milligrams, STAs are not a traditional DSC, so you might have trouble picking up some of the thermal responses. But generally, 2 to 40 milligrams, those are kind of like a sweet spot for most samples. And we typically aim for 10 to 20 milligrams. That's kind of like a nice, happy spot to be in. Whenever possible, you should aim for those. But the difference between having more and less sample mass is that if you have more sample mass, you get better thermal response from your measurement because there's just more thermal mass that's reacting. So you get better resolution when it comes to measurements. But the downside to that is that if you have a sample that reacts back to back, for example, polymeric samples tend to exhibit this kind of behavior, but sometimes they go through crystalline transition and then melting. So if you have really large piece of a sample, those two peaks and valleys might overlap, and that might skew the measurement results somewhat. So in such case, having smaller sample mass is nice so that you can separate out those consecutive peaks. And of course, if you have something that is thermally insulative, like powders or insulation samples, having less sample mass can be beneficial because less sample mass means less thermal gradient within the sample. So no thermal lag during the measurement. The heating rate follows more or less the same logic. So typically you would like to be in 10 to 20 degrees per minute range. If your sample does not call for any special measures, we would typically go for this range, but sometimes high heating rate is desired because it will boost the sensitivity of the instrument. So if your sample is exhibiting that something that is very sensitive, like Curie point transitions or glass transitions, one neat trick to do is to just increase the heating rate so that you get a better resolution from those measurements. But again, on the other hand, you might risk consecutive reactions being overlapped within one another, or creating a huge thermal lag between the sample and the sample pan itself or the furnace temperature. So in such cases, lower heating rate might be useful in such cases. All right, next up we have the calibration requirements. So this is more so for DSC side of things. So strictly speaking, STA does not measure the DSC signal directly. There's a little bit of nuance here. So DTA is what it first measures, and that gets converted to DSC signal. DTA stands for differential thermal analysis, and that really only tells you any information about whether your sample is going through endothermic or exothermic reaction. So you get the shape of the peak that looks like DSC, but you cannot make any comments on the energetics behind it. In other words, you cannot get the heat of reaction from a DTA signal. So in order to convert the DTA to DSC data, you perform something called energy calibration, which some STA models require to be performed after the fact, after the measurement. And a general guideline to this is that you should create the calibration data set using known materials that has similar melt or reaction temperatures to the temperature range that you're measuring a sample in. So, for instance, if my reaction is in the range of 100 to 200 degrees Celsius, these three metals would be your go-to, indium, tin, and lead. And if you're going higher up in a temperature, you'd like to use different metal types. But then again, as you move further down this metal charts, some of them like gold or I believe nickel as well, they form alloys with platinum pans at these temperatures. So when you generate the energy calibration file, please make sure that you use appropriate sample pan types so you don't contaminate the calibration data. And lastly, measurement atmosphere seems like a no-brainer, but it is an important factor to consider. Of course, if you have air in your system and if you bring something up to high temperatures, you're going to see combustion because oxygen will, promote the combustion of your samples. But sometimes that's not desired since you're just interested in inherent decompositions of your material. In such cases, inert atmosphere would be more preferable. All right. Lastly, I'd like to go over some of the advanced STA applications. So these are the state-of-the-art STA functionalities, modifications, and other nice things that you can add to your STA to increase your measurement capacities. And one of the most common configuration with STA is that the STA plus GCMS combination. So in this case, we coupled STA Vesta with Hitachi's GCMS, and we performed an evolved gas analysis of edible oil, so pretty much vegetable oil. So the idea behind this is that, because STA as an instrument measures how the sample decomposes or changes as a function of temperature, whichever gas that gets generated during that measurement can be directly injected into GCMS to then perform, different kind of spectrometry studies. In this case, we performed this on an edible oil, and we got these different spectrums here. For this GCMS, we're using quite a nice one. So you're seeing, electron ionization, photon ionizations, both of them being used to analyze the sample here. And once we compared the NIST, the spectrums we got with the NIST library spectrum data, it reviewed that these components were present inside the oil, and the presence of these components are quite interesting because these are indicative of some oxidations present in the oil. So this is one of the interesting ways that you can use your STAs with. So the next up we have sample observation STA. So this is something unique to Rigaku's STA. The idea is that you can put the sample observation is it is kind of it explains itself really. You're observing a sample as you perform the STA, and the little box here that you see on top of STA here is the camera that's looking down into the furnace directly as you perform the measurement. So I really like this example because it highlights the utility of having this capability. So in this example, we're measuring aspartame under these conditions, and we're seeing lots of back-to-back reactions happening. So you see some mass loss happening in 2 steps before 200 degrees C, but before that, we also see different endotherms, and we see this endotherm here again that does not have any mass loss associated with, but the heavy mass loss here is associated with this endotherm. So you don't really know what's happening to your sample, even though you know the general gist that your sample might decompose somewhere around this temperature. And if you just look at the before and after pictures of the sample, it's really hard to discern when this white powder became this black tarred lump of sample that you see here. So having a sample observation capability allows you to see what's actually happening to the sample at each thermal event. So, for instance, this first endotherm produced some mass loss, but it didn't incur any color change at all. But you see that this middle endotherm here was the culprit for the color change mostly, and from there on, the sample just decomposes rapidly into the tarry substance that we saw at the end of the measurement. So yeah, this is very useful in academic settings, since if you have a novel material that you would like to perform STAs with, it's always nice to have pictures to go along with your data, but also for teaching purposes or in an industry, you can always communicate your data more effectively when you have visuals involved. So it's one of the nice things you can do with STAs. This is a recent addition with Rigaku's STA. So they added something called ChromTA, and that's a chromatic thermal analysis. So the idea is that since they have a sample observation set up already, they added on the color spectrum analysis software package into their sample observation setup. So they can track the different color spectrum as a function of temperature. And as you can see, different transitions of this PET sample corresponds to different color changes. So sometimes we do have sample observation capability in our lab here, and whenever we run client samples, sometimes we get confused as to whether what we're seeing is actually real. But having this kind of color analysis package allows you to give more quantitative analysis on this spectrum changes. And something quite unique to this particular example here, which is PET, is that the glass transition actually causes some spectrum change, as you can see here. So it's quite interesting when you actually have it. You can see the transparency or opacity of the sample just drastically change after that glass transition point, which is always fun to look at. And lastly, we have the dynamic STA, which is, if you're familiar with DSCs, you might already know about this, but one of the novel way to run a DSC measurement is to impose this kind of sinusoidal heat input instead of a linear heat ramp. So with traditional DSC or traditional STA, what you'll be seeing is just a flat curve throughout the temperature. But because we are modulating the temperature across the range here, you're seeing this up and down signal for the sample. And through this data, you can actually calculate the heat capacity of the sample up to very high temperatures. So in this case, we measured a gold sample, about 200 milligrams, all the way up to 900 degrees C. And as you can see, the measured data aligned quite nicely with the NIST literature data. So it's a great options when you have something, when you have a need to characterize CP of a sample to really high temperatures like this, or in cases where you're unsure whether your sample is going to decompose under that kind of temperature atmosphere, since DSCs are meant to be a precision approach to thermal analysis. So if you have any kind of decompositions or combustions occurring with your sample, they would just fry up the sensor that then and there. But with STAs, you can handle most kind of combustions or decompositions happening on the sample holder. So even if your sample decomposes, that's okay. You can just rerun the sample with different temperature ramps to suppress those effects. So yeah, it's a great way to measure CP with these kind of fail-safes implemented, essentially. All right, that's all in terms of today's session. Before we move on to Q&A, I'd like to go through some housekeeping items first. So, just to give a quick shout out to our contract lab testing capability here. So the STA that I mentioned today, along with different thermal analysis methods I showed you today, like STA, DSC, TMA, along with the full Trident sweep, along with the ZFW TIM tester, those are all available within our contract testing lab. So if you're interested in getting your thermal data done with the experts in the lab, feel free to reach out to us using this QR code, or you can reach out to us in the email that we're going to show you today. And lastly, a quick shout out to our partner ZFW. So we are their exclusive distributor in North America, and they manufacture the TIM testers, which is a steady-state based thermal conductivity instrumentation. So as the name suggests, those are dedicated to measurements of thermal interface materials, from pads, paste to plaque-like samples. They really provide a robust solution to those kind of characterizations in compliance with ASTM D5470, which is an industry standard for TIM characterization of thermal conductivity. So if you're interested in those instruments, please follow this QR code here. And lastly, they do provide high temperature heat flow meters as well. So if you're looking for steady state solutions to insulation characterization using heat flow meters, please feel free to learn more about it in this QR code shown here.